Okay, let's pick up from here. Okay, so um, organic molecules can be very simple, like this one here. It's a three carbon molecule called propane, or they can be extremely complex. All you need to do is whenever you get a medicine, open up the little paper inside the box, open it up, and it'll show you sometimes the structure, mostly will just show you the name of the drug. And it's like 5 lines long, very complex. But they can also be very simple. It just depends. Now, in this class, we are not going to be using these type of designations. Okay, we're going to be doing a line drawing. So a line drawing for that three carbon organic molecule there is we are using line drawings. Line drawings are three parts: beginning, end, and a kink. Okay, all line drawings have a beginning and end, but not all of them have a kink. Okay, whenever there's a beginning, there's a carbon. When there's an end, there's a carbon. And whenever you have a kink, you have a carbon. Okay, so we have to come up with a line structure for this molecule here. Okay, so it's got 3 carbons and 8 hydrogens. So beginning on the line drawings, carbon number 1, kink is carbon number 2, carbon number 3 is the end. So this is the beginning, end, kink. Now notice there are no hydrogens there and no carbons specifically detailed. Okay, organic chemists and biochemists have for centuries done line drawings. And so we're going to be using line drawings in this class exclusively. Now, if you have purchased your textbook from 305, you'll notice that the textbook also uses line drawings. This slide presentation is from another textbook, a much better presentation than the slides that come with your book. Okay, so whenever we see this, we immediately go, oh, carbon, 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 and carbon has 4 bonds, and those 4 bonds are taken up with carbons and hydrogens. So here we have this carbon here has 1 bond already. So in reality, it's got 3 more bonds, and those are attached to hydrogens. Here we have this carbon here has 2 carbon-carbon double bonds. That leaves the two remaining as hydrogen. And here, like on the other side, we have 3. So complexity, big difference between the two. Big difference. Now you're going to be quite comfortable with line drawings after a while because you're going to be doing a whole bunch in this class, a whole bunch. Okay, are there any questions about that? This is crucial you understand this line drawing process. Okay, all right, so let's go on. Now, there's a very common concept in organic chemistry and inorganic chemistry, actually. It's called isomerism. An isomer is a structure with the same number of carbon atoms, hydrogen atoms, and whatever atoms, but a different structure. And there's different kinds of isomers. There's geometrical, there's stereoisomers, there's all kinds of isomers, constitutional isomers, etc. But basically, an isomer is just the formula is the same. So if we look at the formula for this guy here, for example, okay, C2H6O. All right, we can write that like that. Okay, so carbon, carbon, carbon. Now, whenever you have an oxygen, nitrogen, with a hydrogen attached, you have to write the hydrogen. Only if it's attached to a carbon, you can leave them off. Okay, so that's one version that fits this C2H6O. Another version, oops, looks like that, where we have the oxygen in the middle and two carbons on either side. So carbon, carbon, and it's the same formula, different structure. One's an alcohol on the left, the one on the right is called an ether, and we'll get into that in unit the third chapter in unit 1. Well, my point is, sometimes if you're given a formula, there are many versions of structures that fit that formula called isomers. Extremely important topic. I mentioned on Tuesday, thalidomide. That was based on isomers of the drug, one being very teratogenic, causing birth defects, and the other caused fixed nausea in first trimester pregnant women. Both same formula, same structures, except one was a mirror image of the other. But they're isomers. Very important. Biologically is more sensitive to these kinds of things than general organic. Biological systems are extremely, can't overemphasize this enough, extremely sensitive to things like, is this left hand, one palm, 5 fingers, right hand, one palm, 5 fingers, but obviously they're not the same at all. Our bodies can recognize that. Organic chemistry sometimes can, mostly cannot. So isomerism, again, is a topic we're going to be covering throughout the semester. Okay. So there's something called functional groups for every class of organic molecule. And the functional groups are things that are kind of hang off the main carbon backbone. They can be things like OH groups, double bonded O's, NH3s, all kinds of combinations. And those are all called functional groups. Now, alkanes, the functional group really doesn't exist because it's an H. And it kind of gets blown in with the other H's on the rest of the molecule. But there are, it says, except for alkanes, each functional group contains a multiple bond for at least one oxygen or nitrogen. Okay, except for alkanes, alkenes, and alkynes. And this is a double bonded, this is triple bonded carbons. Now, alkenes will be covered in our next chapter next week. But anyway, the functional group is what determines the functionality of the molecule. Does it act as a base? Does it act like an acid? Does it act like a oxidative peroxide? What does it do? That's the functional group will determine that. And every group has a different functional group. And I already mentioned we're going to be doing line drawings, not these carbons and hydrogens all over the place. I'm using line drawings. So this is a 1, 2, 3, 4 carbon um, alkane. So we've got carbon, 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 and the H's flow around the carbons. And it's crucial to remember carbon's got four bonds. Four bonds. You only have to know carbon, oxygen, nitrogen, and hydrogen. All you have to know in here. Okay. So the term hydrocarbon, you've probably heard that a lot in the news. I'll talk about hydrocarbon contamination, hydrocarbon this, hydrocarbons that. It's bad for climate change, hydrocarbons. They tend to mess up global warming. Hydrocarbons are extremely common, and chlorinated hydrocarbons are the worst thing we've ever produced. They're horrible. We've gone through many stages of gradually eliminating them in our environment. But the problem with chlorinated hydrocarbons, those are hydrocarbons that have chlorine embedded in them. They tend to last forever. They're the forever chemicals. Have you ever seen that phrase used? They're very bad for the environment. They cause extensive damage to wildlife. For example, birds. It weakens the eggshells, so they don't hatch. That's what happened to the eagles and falcons, et cetera, of the world. Is that the chlorinated hydrocarbons really did a job? The reason why they're so prevalent is because they make great pesticides. My first wife used to work at Davis in the environmental toxicology lab, and she would actually go out in Southern California down by Bakersfield, and where they grew a lot of cotton there. And there's a chemical called toxaphene that they only can use on cotton because it's not edible, except they do feed the hulls from the cotton to cattle that somehow get eaten by us. But anyway, and what it is they take a hydrocarbon and blast it with chlorine. And it ends up being a whole bunch of different molecules. And the insects can't get used to them and form a defense against it because each time they make it, it's different, called toxaphene. It's very effective on cotton. It's extremely detrimental to the environment, however. Chlorinated hydrocarbons, bad stuff. Okay, so there's a couple terms here I'm going to talk about. One is saturated and unsaturated. Now, saturated means no double bonds or triple bonds. Unsaturated means double bonds are present, one or many. Triple bonds are present, one or many. Now you'll hear saturated and unsaturated fatty acids, for example, all the time in nutrition. That has to do with the chain on the end of the fatty acid, whether it's got a double bond in or not. That means it's unsaturated. Saturated fats are the most, have the best mouthfeel. Typically, they come from animals as opposed to plants. Things like stearic acid, palmitic acid. There's a number of fatty acids that are saturated that are not very healthy for you. Unsaturated fats, like oleic acid, have one double bond in them, and that's considered an unsaturated fatty acid. They also have polyunsaturated fatty acids, which contain multiple double bonds. So this concept of saturation is used a lot in the health industry. Okay, now this class is designed for allied health. We have, in our body, we have no triple bonds of carbon. That class of chemicals is called alkynes. We're not covering those. We're only covering alkenes. Alkenes are very ubiquitous in our bodies. They're all over the place. Aromatics. That's a special breed we're going to talk about next week. Aromatics are a special combination of single and double bonded molecules. And they're very, very, very stable. That's why they form these particular structures. And those are very prevalent in our bodies also, very. So we have, for this first part of this unit, we have alkanes covering today, alkenes we're covering Tuesday, and then Thursday we're going to touch upon alcohols. So moving along, basically a lecture per functional group. Okay, they like to go in and talk about these clever little formulas for determining the number of different uh, uh, different versions of the molecule based on how many carbons there are. Yeah, you can go on, but that's not important at all. Important thing is to realize that uh, uh, alkanes are non-saturated. Only carbon-carbon and carbon H bonds are there. You don't need to worry about how many different versions there are. Now you're going to be naming in this chapter, we're going to be naming compounds, and those okay, let me okay. So we're not talking about hydrogen. You're just looking at the carbons here. Um, there are different ways. We have 4 carbons, 5 carbons, I guess, and we can connect them up in a variety of ways. If we connect them up in a long string, that's called normal. If they're not connected up in a long string, they're called branch. Now, in my class, about 16, 17 years ago, one of my students came up with a way to differentiate between something called a backbone, a carbon backbone. And she used a highlighter. So what she would do, she would take and highlight the backbone. And that's going to, if you follow that process, I'm going to be using it throughout the whole semester. You'll find that naming compounds is a lot easier. Because when we start naming, we need to know what compounds are, what is on the backbone, what's off the backbone. And if you use a highlighter to highlight the backbone, what's off the backbone is immediately obvious. In this case, we have 2 carbons off the backbone on that branched alkane there on the right. And you'll see as I talk today how this comes into play. Okay, now, this is something you need to know. Carbon-carbon single bonds rotate freely. Okay? Rotate freely. There's no rigidity. What I mean by rigidity means it won't rotate. So if we're looking at we're looking at these two molecules. Okay, 4 carbons, and the two middle carbons are connected with a single bond, meaning freely rotate. So the question is, between these two versions, the one on the right is rotated a little bit. And what will happen in nature, we'll always seek out the most stable version. So which is more stable, the one on the left or the right? One on the right, why? Yeah. Now what happens to the one on the left? The two groups up here have some tension there. And remember, there's a bunch of electrons associated with these things. Electrons do not like to be around other electrons. So by twisting that carbon, that blue carbon, we've actually moved that this group up here downward so that it doesn't interact with that other methyl group. The fancy name for this is called steric hindrance. So steric hindrance is when two groups are too close to one another. Nature doesn't like that. So what happens is the conformation of the molecule changes to minimize that conformation, that where you get the hindrance there. And that's exactly right. Very good. Now, this assumes we have the ability for that bond to be able to rotate. If the bond can't rotate, then you're stuck. So this would be the same kind of deal. Okay, these guys can rotate around, and so this would be the least because we have the steric hindrance right here, and this would be the most stable. And again, nature likes stability. Nature likes stability. Nature likes symmetry. Remember those two things, stability and symmetry. Because we're going to be doing reactions. And with reactions, you frequently have multiple products produced. The question is which of the multiple products is more stable? Well, there's some rules we go through. One of them is which is more symmetrical. Symmetry wins. Nature likes balance. The other one has to do with something called a Markovnikov rule, which we'll get into. But again, this underlying symmetry throughout this course, you'll see, is a good thing to rely upon in determining stability. Okay, so let's look at okay, this is all 5 carbons, right? So the first thing you need to do when you start naming alkanes is to figuring out the backbone, like I mentioned earlier. Okay, so you take your highlighter, and which is the longest you can draw that contains them all without lifting your pen. Okay, so that one there, that's a long string, so that's the main backbone. Look at this one down here, however. Okay, 4 carbons long, and we have one off the backbone. Now you can also draw this like that. Both those are valid backbones. Now, both of them have 1 carbon off the backbone. The carbon off the backbone is called a branch. So branches are carbons off the backbone. Yeah.
What is the purpose of identifying the backbone?
That'll be part of naming. There are three parts to naming. The middle part of naming is how long is the backbone? So you need to know, you have to identify the backbone. And number two, how many carbons does it contain? And that'll be like di, tri, meta, tetra, penta, refer to that. That's why you have to identify the backbone. Okay, let's look at this one over here. Okay, well, we've got, oops. That's one backbone, 4 carbons long. And we've got one branch off of it. That's another backbone with 1 carbon off. And you can choose either one. Either one is fine to use as a main backbone. So the 2 top ones have no branches. 2 bottom ones do. Okay, so a branch is a carbon off the back. Now you're going to be doing this forever in this class. You're going to be identifying backbones and branches and all this stuff. Now, the reason why these 2 molecules are the same molecule is because the single carbon-carbon single bond can twist. So we can twist the one on the left to be equal to the one on the right. It's got the same number of carbons. It's got the same backbone. So it's the same molecule. They're also called normal because they're non-branched. Remember, there's normal and branched. Normal is no branching. Branch means there are branches. So the question is, are these molecules a molecule? Are these
Sorry, I didn't hear what you said. Did you
I
say
said, are these molecules the same molecule? They don't look the same, but they are. The reason why they are is we look at the backbone. 4 carbon backbone. 4 carbon backbone. Where is the branch? Bless you. Where is the branch? The branch is on the second carbon. Second carbon. And the branch is 1 carbon long. So these are the same molecule. Notice that I counted from the back on the right-hand molecule. So you can start from the left or the right when you're numbering. Left or the right. Because we can flip those in space very easily. Okay, so 2 things. The backbone is the same number of carbons. Number 2, the branch is on the same number carbon. In this case, carbon number 2. That means it's the same molecule. That means it's got the same melting point. It's got the same chemical characteristics, physical character, etc. It's the same molecule. Okay. Now, this is something that you're going to eventually know inside and out without having to memorize it. In the beginning, you're gonna have to memorize it, but by using lots and lots and lots of practice, you won't have to memorize it. By very use of it, you'll get to know it. Okay, so whenever we have a branch, we use slightly different naming conventions than if it's a backbone. Okay, if it's a backbone, we're using the if it's a one carbon backbone, that's called methane. Two carbon backbone, no branches, it's called ethane. And then propane, butane, pentane, hexane, heptane, etc., all the way up to 10. If we're naming the branch off of the main backbone, it's slightly different. We go into a adjective form. Okay, so if it's a one carbon branch, it's called methyl. Two carbon branch, ethyl. Three carbon branch, propyl. And on propyl, there's two ways we can attach that branch via N-propyl and isopropyl. You've heard of isopropyl alcohol. Okay, isopropyl alcohol has got an isopropyl group in the alcohol. Okay, so main backbone, we're using the ANE. And if it's a branch off of the main one, we're using the YL to distinguish it. I'm going to get showing you lots of examples here in a minute. Okay. 4 carbons long. Butane. Butane can be in 4 different versions. N-butane, isobutane, and then if it's a branch, it can be butyl, sec-butyl, and that depends again where it attaches, isobutyl, and T-butyl. Now again, I'm going to show you how all this fits together in a minute here. And then there are common branches that are not carbon necessarily related. Okay, and we have and these are the main two: chlorum, bromo, more chloro than bromo. You'll see a lot of organic compounds with chloro in it. And then later, as we go into the term, we'll have nitros and aminos and some other things. Okay, so IUPAC, International Union of Applied and Pure Chemists. It's the official way to name things. And then there's the other way to name things called a common name. So you've got common name, IUPAC. The problem with IUPAC, if we're in Mexico, Russia, Israel, or United States, the IUPAC name is the same. The common name is not. For example, ¿cómo se dice water in Espanol? Agua. It's not water, is it? Okay, but the IUPAC name for water is dihydrogen oxide in Mexico, in Russia, in Israel, and the United States. That's the IUPAC name. Now, IUPAC seems, well, why doesn't everyone use IUPAC? Okay. Water. Who wants to call water dihydrogen oxide or monoxide? Well, unless you want to fuss around with your parents or your friends, call it water, right? Or aqua or whatever. Okay. The problem with the IUPAC name is it tends to be more clumsy. In fact, again, going back to the drugs you get, when you open up that little paper, it'll tell you the IUPAC name for your drug. And it is really, really long. It's 5 lines, typically 5, 6 lines long. You can take a whole course on naming compounds, a whole course. So it's quite comprehensive. And we're going to be naming things with both common names and IUPAC names. But our IUPAC names are going to be much shorter than five lines long. Okay, so all right, so let's talk now about the IUPAC method. For our class, we're going to be using 3 parts most of the time, sometimes 2 parts. This is optional over here. That applies to the branching. If there's no branching, you can disregard that. Okay, so all of them have a root and an ending. The root has to do with how long is the longest carbon chain. 4 carbons, 5 carbons, whatever. Ending has to do with the functional clasp. That's that little group that hangs off of the main backbone that gives that molecule its characteristic chemistry. Prefix has to do with any branching. Okay, and we need to also understand that we have a prefix that's keyed into the number of groups, whether it's carbons or functional groups or whatever. This you need to know. You'll be using that every day. And you won't have to memorize it because you'll be using it every day and you'll automatically get to know it. So and notice there's a dash there. So these are like prefixes. It'll determine, for example, if we can have methoxide. That means 1 oxygen. Pentoxide, 5 oxygens. And you need to know all the way up to 10. We're not going to use 9 and 10 very much, but you need to know up to at least 10. It goes on forever, though. But once you get past 10, it drops off precipitously. Okay. All right, so that's number 1, is how many things are on each part up here. So each part can have a 1 carbon, 5 carbon, or whatever. Each part can have 1 functional group, 5 functional groups, and all of it has to do with the way they name the number is through these prefixes here. It isn't just carbon atoms either. It has to do with number of groups, whether it's carbon atoms or functional groups. You can have a diol. Di meaning 2. OL is alcohol, a diol. That's 2 functional groups. I'm going to get to alcohols next week. Okay. All right, so let's name this guy. Okay. Step number one is always look at the backbone. What is the longest carbon backbone? Well, you can go like this. You can go like that. You have a choice, pink or yellow. Both are valid backbones. So let's go with the pink one. Okay, and how long is it? How many carbons long is it? It's 5 carbons long. Remember, there are 3 parts to name it. So the middle part is how long is the carbon chain? In the case of hydrocarbons, the functional group is just H. So that is a ANE. Okay. So the second thing is name the functional group. And for this chapter, it's ANE. Now the next one is, do we have any carbons off the backbone? We do. Okay, we have 1 carbon long. Now the question is, we have to name the carbon it comes off of. Now, here's where it can get tricky, is we have to number this from the left and the right. So we now have a choice. It's either coming off of carbon number 2 or carbon number 4, which is correct. Now, in this class, it's always the lower number. Always the lower number. Okay, we're going to see this throughout the naming. Always the lower number between the two. Okay, so we're going to disregard the red numbers because that'll put the branch at 4 rather than 2. So we're going to get rid of the red numbers. Does everyone see why we're eliminating the red numbers? It gives us 4 rather than 2. So let's get rid of the red numbers. So we're going with 2. So we have to say now, part 3 is, that's right here. Number 1, what is the carbon number that the 1 carbon came off of? 2. Carbon number 2 on the backbone. So that's 2. And how many carbons is it? 1, 2, 3, 4, 1. So it's methyl. So it's 2-methyl pentane. Okay. 2-methyl pentane. 3 parts most of the time. Occasionally you'll have one with no branches. But always think 3 parts to start with. Now, you may write it like this. Or you may write it like that where you're separating it. I like to separate it so that it stands out more. But you can write it either coupled together or separate. Either way, it's fine. Okay, are there any questions about this? Now, this is your first naming. Now, every chapter is going to have naming in it. Every test will have naming in it. I'll give you a structure, name it. I'll give you a name, draw me a structure. Every test. All right, so let's do some more here. Are there any questions about this guy? All right. Let's look at this guy here. And let's simplify it a little bit here. Let's okay, so we've got this guy. Step one is backbone. There's a lot of different ways to draw this. The way it's laid out is looks like it's the best. So that's there. And remember now, when we draw the backbone, two numbering systems. We have the black ones right now, and we have the red ones. Okay, so that's 7-carbon backbone. Yeah.
Because I see that it's left to right already, so why did you write the numbering right to left?
You have to do both. Because we're going to see which numbering system gives us the lower numbers. That's why you have to have both. Okay, so question number one is 7-carbon long backbone. Number two, are there any carbons off the backbone? We've got a couple onesies and a one twosies, right? Okay, does everyone see that? Okay, so we start by, okay, a 7-carbon backbone is hepta. And it's a hydrocarbon, so it's an NAE. Now, branching. Okay, we've got some ones and we have some duals. Okay, so the onesies are methyls. The double one is an ethyl. Okay, so we're going to go dimethyl. Methyl is one. Di means we have two of them. Ethyl. Heptane. Now we have to number the carbons on the backbone from which the branches come from. So we have, well, carbon number 4 is, doesn't matter which way we name it. Carbon number 4, we get the ethyl group. So that's going to be carbon 4 for sure. So that's 4-ethyl. This is irritating. Okay, so that's gonna be definitely 4-ethyl, because it doesn't matter which direction we're naming it, it always ends up on carbon number 4. However, the methyls depend a lot on which you're using, the red or the black. Okay, we could either say 2,3-dimethyl using the black numbering, or 5,6-dimethyl. Now, from what I said in the past, which you think we're going to use? 2,3, because it's lower. So that means the red numbering gives us the poorest name. Now, on a test, for example, if you gave me, I said to name this guy, and you said 5,6-dimethyl 4-ethyl heptane, I would ding you 1 point. Now, the reason why I'm focusing on naming is so that you focus on the structure. So if you named it correctly, but not as correct as it could be, you still are focusing on the structure. So you met my needs, but I can't give you full credit because you didn't name it right. I'm giving you partial credit. Now, the name of this class is no multiple choice questions, because I can't give you partial credit. If it's a fill-in, I can give you partial credit. So I only give fill-in tests. Okay, so this answer is going to be two, 3-dimethyl 4-methyl heptane. Okay. So you're going to make some decisions on numbering. And you'll find in this particular chapter on alkanes, you'll find the most variance on numbering. After a while, it kind of falls out so that it isn't as tricky. But in the beginning, the combinations tend to be tricky. Okay, are there any questions about that? Yeah.
So how did you?
Oh, because I messed up. That's why. Better. Thank you. Now, everyone, I already told you I'm old. I prove I'm human every day. How many times have I been doing it today? But 4 times now. We need the technology to work. Okay. Any questions about? Yeah. Yeah.
Why is the 4-isopropyl first?
Okay. So we're not done yet, actually. Not done. Okay. All right. So we've already determined numbering. We minimized the numbering, right? By using the black numbers rather than the red numbers. Okay. There's another issue in the IUPAC naming is what is the order of the branches? We have methyls and ethyls. Which comes first? Okay, alphabetically is which comes first, E or M? E. So the ethyl comes first. So that's the official name. So we want lower numbers and alphabetized. Okay. Now, it doesn't get much harder than that one. Now, one thing about alkanes, alkenes, all the groups, we can have non-cyclic, we can have cyclic. Now, I mentioned that single carbon-carbon bonds can twist naturally. Cyclic carbon-carbon bonds cannot twist naturally. So there's rigidity. Now, in this class, whenever you have anything rigid, red flag should go up. Because then we can have isomers. So that's a big deal when we have rigidity. Not all the time, but frequently we'll have isomers, two isomers that can exist because of the rigidity of the structure. And we're going to see that with double bonds and with cyclic single bonds. Now, to name a cyclic, we're going to call a 3-carbon cyclic compound cyclopropane. And there are numbering as well, because it's considered a backbone. So as soon as you see the cycling there, it's automatically backbone. Auto backbone if it's cycling. A 6-membered ring is the most stable. So in nature, you'll see a lot of 6-membered rings. Glucose, for example, is a 6-membered ring. Fructose is a 5-membered ring. Not as stable as glucose, but it's still a fairly stable. As you get lower than that, however, this is extremely not stable. Extremely not stable. In fact, the more unstable the compound is, the harder it is to synthesize. So, trinitrotoluene, TNT, it's extremely unstable. That's why it likes to explode. So it's really hard to manufacture. It's also hard to transport. And a guy got a Nobel Prize for making dynamite using TNT. He made it more stable. Nobel Prize. And guess what his name was? Nobel. Dr. Nobel. He invented dynamite. Everyone's going, dynamite. But they had horrendous explosions with pure TNT. They built the Transcontinental Railroad with TNT, not dynamite. Wasn't invented at the time. So when they were blasting through the hills out of Sacramento, those were all done with TNT. Many, many, many lives were lost because of that. But when you're blasting through solid granite, the only thing you can do is use something really strong and TNT fit the bill. But even moving it to the site. On a wagon, it would blow up. It was bad stuff. Yeah.
Because cycloalkanes are rigid, like if you had a branch on the inside, it couldn't like flip outside.
Um, it'll it'll naturally flip to whatever is more stable. So yes, it can actually do that, but it'll flip flop around and then it'll spend most of the time in the more stable version, in the unstable version.
Okay. So what do you mean by that they're rigid?
Um, the carbon-carbon bonds can't spin, can't twist.
Okay.
They can turn themselves in and out, but the relationship between I love humming. I have tons of pictures of hummingbirds. My late wife and I used to have our backyard. We I probably have 2,000 pictures of hummingbirds. I really love them. They're very aggressive little guys too. Yeah, they're very, believe it or not, they're just badass little birds. Okay, so anyway, the relationship stays the same though, even though it flips in and out.
Yeah, twist in relation to each other on
Yeah,
one by
so it
one,
can't
but-
change the relationship between the like if we had
Oh, yeah. It can twist as like a unit, but not.
yeah, so if we had an H and a Cl there on that one top carbon, that relationship to this is not going to change. It can flip in and out, but if it flips in and out, the relationship will remain the same. Good question. Okay, so cyclic compounds are very common in organic systems, particularly. So to name a cyclic compound, the cyclic compound automatically becomes the backbone. So we have a backbone, boom. Don't even need to think about it. All right. So how long is the backbone? Well, we have 1, 2, 3, 4, 5 carbons long. And it's a cyclo. Now we have a 2 carbon and a 1 carbon branch. The 1 carbon branch is a methyl, 2 carbon branch is an ethyl. So we have to number the backbone, just like before. I'm going to name it 2 different ways. Going this way. And we're going to go this way. Okay. So we can name it by cyclopentane is the backbone. And then we can name it by looking at the blue numbering. Let's look at that. That's going to be 1 ethyl, 4 methyl. If we use the black and red numbering, it's going to be 1 ethyl, 4 methyl. So which is correct? They're the same, right? Easy. They're both the same. So it doesn't matter which way you number it on this one. Actually, let me back up here. This is screwed up. Um, yeah, let's redo this. 1, 2, this is 3 here. 4, 5. Okay, we do the blue numbering. It's 1, 2, 3, 4, 5. Okay, so it's going to be 1 ethyl. We're using the blue numbering. 4 methyl. We're using the black red numbering. It's going to be 3 methyl. So that one wins out. So it's going to be 1 ethyl, 3 methyl cyclopentane. When you do your numbering, make sure you put the numbers right by the carbons, not like that. That's what messed me up there. But again, it's the backbone. You name it, number it 2 different ways. Pick the numbering that gives you the lower number. Ethyl before methyl, alphabetically. Okay, any questions about cyclocompounds? Yeah.
Test, or do you expect us to remember all of them too? Like the condensed formulas where it shows like the triangles and the squares and stuff, like it does right there. Do you expect us to know by name that that's a cyclopentane?
Yeah.
Okay.
You know, and you're going to recognize the shape of the ring because 5-membered rings look like kind of a collapsed house, and 6-membered rings will look like this. So you immediately recognize that blue one. Oh, that's a hexa. And that one. And you can also draw this guy as a non-collapsed house like this. Okay. Now, I mentioned this rigidity thing. When we have rigidity, we can have the possibility of isomers. So if we're looking at a 5-carbon ring on the left, 5-carbon ring on the right, with 2 methyl branches on either one, you can have 2 versions of that molecule because the carbons can't twist naturally. And it forces them to either be both down or opposite. If they're both down or both up together, it's called cis. If they're opposite, it's trans. Now, you've heard that in relationship to fatty acids. Trans fatty acids, cis fatty acids. Trans fatty acids are unnatural. Cis fatty acids are the natural way that our body produces fatty acids. Our membranes are designed for cis fatty acids, not trans. So if you have a lot of trans fats in your body, it screws up your membranes, your cellular membranes. Now, your body is a sack of water separated by membranes. That's how your body keeps all the reactions separate by membranes. If your membranes are messed up, your reactions are not going to be kept separate. Hence, they're not going to function properly. That's why it's extremely important to have non-trans fats in your diet. Okay. We're going to see this cis-trans throughout the semester, but this is your first exposure to it. Think of the word cis as in sister. Sisters can be close, not all the time. And trans, think of transcontinental, kind of far apart. Okay. All right, physical property. First of all, let's back up here. Are there any questions about naming? Okay, your dry lab number 1 has got a lot of naming practice in it. Dry lab number 2 has got naming and reactions. Okay. Now, we're going to be talking about something called intermolecular forces. Intermolecular forces are the forces between molecules. Thought I was doing pretty well today. And alkanes have very weak intermolecular forces. Now, in next unit, not the next unit, the next week on Tuesday, I'm going to talk more detail about intermolecular forces. But intermolecular forces between alkanes are very weak. Hence, they have a low boiling point. So I abbreviate that with IMF. And by the way, every test will have questions on naming, IMF, and reactions. No exceptions, every single test. Except the last test, which is, the last test, by the way, is open book, open notes, open whatever, open internet. Okay? Now, most people find the last test is the hardest, even with open book, open notes, open internet. It's called carbohydrate metabolism. We're going from glucose to adenosine triphosphate, ATPs. All the little steps, and there's a bunch of little steps. And what are the reactions along the way? And what are the names of the enzymes along the way? So anyway, okay. Okay, so intermolecular forces are directly related to boiling point, melting point. Usually people talk about boiling point as opposed to melting point, but it's the same thing. And surface tension. So for example, water has a very high IMF. It has to do with its hydrogen bonding. It is so strong that insects can land on the top of the water and walk on it, like mosquitoes and water striders. And that's because high intermolecular forces. Now, if that mosquito should land on a hydrocarbon, guess what? It can't walk on it because the intermolecular forces are very, very low. Now, when I lived in Florida, as I was in junior high back in the early 60s, I lived at Homestead Air Force Base. That was below Miami, and we get rain all the time. And when you get rain all the time in Florida, you get something called mosquitoes all the time because they love to breathe. Well, the base would come on our property and fill in any puddles of water with gasoline. Gasoline floats on top of water. So when the mosquitoes land on the gasoline, they go bubble, bubble, bubble. That was the base along with DDT. Every day we used to get our neighborhood fumigated with DDT for the mosquitoes. And guess what us little kids would do in the neighborhood? We would run behind the fumigator to the white fog of DDT. I'm not exaggerating. We thought that was the coolest thing. Now, you know what how that screwed up my body? Big time. But anyway, that's what the basis solution was to put gasoline on all the puddles. And it worked, but what they did in those days is incredibly bad. Really bad. And we've cleaned things up so much. There's a lot to do still, but we cleaned up so much. Okay, so the stronger the IMF, this is directly proportional. Directly proportional. And there's also indirectly proportional, which means when one goes up, the other goes down. This is direct. One goes up, the other goes up. IMF goes up, boiling point goes up. IMF goes up, surface tension goes up. So I will give you on a test a series of chemicals. And you're to look at those chemicals and determine the IMFs, and then determine which has the highest and lowest boiling point based on your determination of the IMFs of those chemicals. Now, we can't do it now because we don't have enough diversity, but when we get to alcohols and ethers, we can start doing that then, and we will do that in lecture. Okay. So this is the main thing. It's a universal truism. IMF goes up, boiling point goes up, surface tension goes up. Now, if we have the same type of molecule, if the molecule is bigger, its boiling point will be higher. So if we have a 1 carbon methane and a 5 carbon pentane, the pentane is going to boil higher than the methane because 5 is bigger than 1. So you have two phenomena going on. You have the interaction, intermolecular forces between molecules, and then you also have the physical size determines it also. So if you have a whole series of alcohols, for example, the only difference between the alcohols is their number of carbons on the backbone. The one with the most carbons has the highest boiling point. Now, this particular graph, I'm going to redo for every single chapter. I'm going to keep adding stuff to this graph. Now, this is a graph of boiling point versus number of carbon atoms. So as the number of carbon atoms goes up, boiling point goes up. We're going to find that, for example, we're going to find alcohols are way up here because they have higher intermolecular forces to start with. Hence, the boiling point is going to be higher. And as the number of carbons increase, the boiling point also goes up. And then we're going to find there are ethers and acids. So we're going to find a whole series of these graphs as we progress through this course. Okay, now this is something that is a hot topic, and I've decided to leave it off. It's called bond hybridization. It even sounds awful, doesn't it? So we're not going to worry about bond hybridization. And I should just take these slides out. Okay, now, we haven't talked about reactions at all yet. The good news on this chapter is there are only two kinds of reactions. Combustion and chlorination. It's two reactions. Now, all organic compounds, I think without exception, almost all of them anyway, burn. So they all undergo combustion, not just alkanes. And that's important to understand because a lot of books leave out, once they pass alkanes, they forget to mention the combustion still goes on. Now, oxidation, I know you covered in 305. Who remembers what oxidation is? Does anyone remember what oxidation is? Yeah, it does in an indirect way. And decomposition. Okay, so oxidation, you guys are close, but not right on. Okay, oxidation. The loss of an electron. Or
I don't think everybody realizes.
you don't want to try it for free. Thank you. Okay, I don't know what to say. Okay, all right, so in inorganic chemistry, oxidation is a loss of electron. In organic chemistry, I want you to think loss of hydrogens. We're not going to see a lot of electrons flying around in organic chemistry. We're going to see a lot of hydrogens gained or lost. Okay, so if we lose hydrogen, it's oxidation. What's the opposite of oxidation? Anyone remember? Huh? Reduction. Exactly. So that would be a gain of an electron and a gain of hydrogen. So this is a real simplified version of it, but it works. You don't need anything more than you really don't. Okay, so first reaction we're going to talk about is combustion. Alkanes are used as fuels all the time. Methane, comes out of the wall for your stove. Propane is used in gas grills, butane lighters, etc. Gasoline, diesel, all that are hydrocarbons in combustion reactions. Now, combustion any of these plus oxygen yields carbon dioxide and water. Doesn't matter whether it's methane, ethane, pentane, uh, hexane, octane, dodecaine. Doesn't matter. They all go to carbon dioxide and water, assuming there's enough oxygen around. Now, who's seen a campfire? Gosh, everyone's raising their hand. What color is the flame? Orange. Okay. Who's seen the flame on their gas stove at home? What color is it? Blue. They're both burning alkanes. Why is one orange, one blue? Oxygen is the key. How much oxygen is given to the alkane to burn? If you have enough oxygen, it goes to carbon dioxide and water. If you don't have enough oxygen, what happens is you have something called flaming carbon. That's carbon without an oxygen. And guess which color it burns? Yellow. So when you're on a campfire, what you're seeing, that nice romantic ethereal flames, that's flaming carbon. Also, who's cooked over a campfire before? Okay, what color is the bottom of your pan? Usually black. That's because the burning carbon is adhering to the bottom of your pan, because it's not burning completely. On your gas stove at home, when you cook with a gas stove, is the bottom of your pan black? No, because there's no flaming carbon. Blue means it's burning very effectively, very efficiently. So, with enough oxygen, it's key. Now, when a person comes in and adjusts your hot water heater, for example, which is usually gas fired, there's something called a jet. And there's a little adjustment there to allow more or less oxygen into that jet. So what they do is they adjust it till the flame is pure blue. That's the most efficient way. And it's the most efficient way of transferring electrons. Because transferring electrons means a reaction's going and giving off energy. Okay, so reaction number one, combustion. It's also probably the easiest reaction. Reaction number two is halogenation. And usually it's chlorine or bromine specifically. Halogenation. So if we have an alkane, like 1, 2, 3, that's propane, plus chlorine, with UV or heat, those are the conditions. So every reaction's got three parts. Reactants, which you start with, product, which you end with, and the conditions. So on a test, when I ask you for the product of this reaction, you have to give me and name the reactants, name the products, give me the product, and the conditions by which that reaction happened to get full credit for the reaction. Okay, and so this is a good example of a reaction. Okay, so I have 1, 2, 3, 4, 5. So that's pentane. We name it. Name the reactants. The conditions are heat and UV. It yields a chlorinated hydrocarbon. Now, you're going to get a mixture, but all you need whenever this reaction goes is a chlorine someplace along the backbone of that pentane. You can have it here, you can have it here, doesn't matter. And then we have to name it. So let's name it. Let's name that one. Yeah. What?
It's 220. Class says it's 220.
I'm still not connecting. What?
It's class over at 220. I'm talking about the time.
Oh, well, the class is officially over, but let me just finish this one. We had all those technical difficulties. Okay, so let's name this here. Okay, it's a 5 carbon backbone, and we have a branch at carbon number 2. So it's going to be 2 fluoropentane. Okay, so that would be full points. Not reaction. Okay, we name the reactants, we name the product, and the conditions. Now you're going to find reactions are the trickiest part of this class. I've been doing this class, I've taught probably 45 of these throughout the years. And every time, no exceptions, students go, this class wasn't too bad except for the reactions. And you're going to get synthesis problems like, or you can get problems like this where I give you starting place and some conditions, what happens. Or I will say, how do you make this? Either way. Okay, so we're going to go over some more examples on Tuesday. So, so Tuesday lab people, I'll see you next week, and Thursday lab people, head on over. And there should be no one in the lab. Well, of course, you don't have a key to get in.
You should